the slope and y-intercept of the least squares regression line. Our objective, interpret the slope and y-intercept of the least squares regression line, also known as the line of best fit. Let's remind ourselves what we know. Okay, we know the equation of the least squares regression line is y hat is equal to b sub 1x plus b sub 0, or we can switch these two and you get y hat is equal to b sub 0, the y-intercept, plus b sub 1, the slope, times x. Okay, y hat is used to remind us that this is the predicted value. Okay, the slope is the change in y per 1 unit of x, and the y-intercept is the value of y hat when x is equal to 0. Again, take you back a little bit to your algebra days, working with lines and the equation y equals mx plus b. Let's talk about how we interpret the slope and y-intercept in statistics. The slope is the change in y per 1 unit change in x. In statistics, the slope is interpreted as on average. Again, statistics is never about precise, excuse me, and when it comes to the slope, we're talking about on average. So for example, if we're comparing the slope, if we're comparing the golf club head speed to how far the ball travels, and we come up with a slope of 3.166, we could say one of these two things. If the club head speed increases by 1 mile per hour, 1 unit change in x, the distance the golf ball travels increases by 3.166 yards on average up here, okay? Or if the club head speed increases by 1 mile per hour, 1 unit change in x, the expected distance the golf ball will travel increases by 3.166 yards, the change in y. So that's how statisticians talk about the slope. It's a unit change in x, and then they talk about a increase or a decrease in the y, depending upon if it's positive or negative. How do we interpret the y-intercept in statistics? Well, we only interpret the y-intercept if 0 is a reasonable value for the explanatory variable. And we'll talk about that in our example. And if we have if there are observations that are near x equals 0 in the data set. Okay, we need to have observations near that in the data set. And I'm going to go back, I just forgot. I'm going to go back and get that data set out of here so we can take a look at that data set that we're going to make use of. In fact, in general, we should not use the regression model to make predictions that are outside of the scope of the model, outside of the data that we have. And we'll see that in our example as well. Okay, let's do the example. I think this will make a lot more sense once we've done that. Okay, get myself straightened out. There we are, I think. Example 1, and we saw this example in a previous lecture. A pediatrician wants to determine the relation that exists between a child's height and his or her head circumference, both of which are in inches. She randomly selects 11 children from her practice. She measures their heights and their head circumferences, and she obtains the data, which is in 4_2_19. And I will quickly show you that. This is the data we saw. And again, we saw this in a previous example, 4_2_19. And here are the heights of the 11 children and their corresponding head circumferences. Okay, as we previously calculated, we came up with the equation of the least squares regression line. And it is y hat is equal to 12.493 plus 0.183 times x. And we want to interpret the slope and the y-intercept if appropriate. Okay, the slope. Okay, the slope is The slope talks about per 1 unit increase in the x, which in this case is the height, what is happening to the y. So if height, which is the x variable, if height increases by 1 inch, there's a comma there, the head circumference increases by about, and here's our slope, right here's our slope, 0.183 inches on average. Remember, I had that in bold on the previous page. Okay, so the slope, a 1 unit change in x, a 1 inch change in the height, results in an increase of about 0.183 inches in the head circumference on average. Okay, how about the y-intercept? Okay, let's first note the y-intercept as a point is the point 0, 12.493. Okay, that's the point, which means a 0-inch tall child has a head circumference of 12.493 inches. Okay, guess what? That makes no sense at all. A child of no height has a 1 foot head circumference. Makes no sense at all. So, not only is this not reasonable, which is one of our criteria for the y-intercept. This is not reasonable, okay? It is also outside of the scope of the model. Let's take a look at our data to see that. Okay, our model is based upon this data. Okay, and this data, the heights go from a low of 24.5 inches to a high of, it looks like, 27.75 inches. Okay, so there's no data point anywhere near a height of 0 inches. So 0 inches is outside of the scope of our model because it's not within our data set. And so we can't use it to make predictions because we don't have any data here that will allow us to be close, that incorporate something close to that. So not only does it not make any sense, it's also not, it's outside of the scope of our model, okay? Okay, part B here. Come up a little bit for you. Would it be reasonable to use the least squares regression line to predict the head circumference of a child who is 32 inches tall? Why or why not? Well, let's take a look at what our model is based on. All right, our model is based on children whose heights are between 24.5 inches and 27.75 inches. 32 is outside of the scope of this model. I guess we could use it and we would get some information, but it's not, 32 is a solid almost 20% above our tallest child in the data set. So it's kind of out there. It's really, this line might not be the best thing to use. It'll give us an answer, but the answer might not be very good because that child's height of 32 inches is outside. So we're going to say no. Okay, it's not reasonable. Okay, would it be reasonable? No. Why or why not? Because a 32-inch child is outside of the scope of the model. Okay, so keep a couple things in mind. I'll go back to the front page here and recap. Keep a couple things in mind that are key here. As you're dealing with slope, you're dealing with per 1 unit change in the x variable. And we're always talking about it being on average as we predict it, use the equation to predict. And when we're dealing with the y-intercept, we can only use the y-intercept if 0 is a reasonable value for the explanatory variable, and if observations near x equals 0 exist in the data set. And then as we saw in part B, in fact, we should not use the model to make predictions that are outside of the scope of the model. We want to make sure we are within the scope of the model.